Hi everyone, Assalamualaikum and a very good morning. So today we are going to continue with our tutorial. So we are going to continue with chapter 6 chemical equilibrium, subtopic 6.2 equilibrium constant part 1. Okay, so since this is like a lot of topic for subtopic 6.2, so I divided it into two parts, which is part 1 and part 2. So we are going to look at the part 1 first. So these are the learning outcomes that we are going to look at for this equilibrium constant part 1. So the first one is we are going to define the homogeneous and the heterogeneous equilibria. And second one, we are going to write expressions for equilibrium constants in terms of concentrations Kc and the partial pressure Kp for homogeneous and heterogeneous systems. And lastly, we're going to use the equation Kp equals to Kc RT to the power of delta n to solve the equilibrium problems. So without further ado, we are going to start now. Okay, so now there are two types of equilibrium reaction. So the first one is homogeneous equilibria and the second one is heterogeneous equilibria. Okay. Alright, so what is homogeneous equilibria and what is heterogeneous equilibria? So homogeneous equilibria is the reaction in which all reactants and products are in the same phase. So for example here, we have N2O4 gas decomposed into NO2 gas. So both of the reactant and products are in the same phase, which is the gas phase. And for example, we have SO2 gas react with oxygen gas to form SO3 gas, and all the reactants as well as the products are in the same phase. Okay, so this is what we call the reaction is in the homogeneous system or homogeneous equilibria. However, for heterogeneous equilibria, the reaction is in which the reactants and products are in different phase. Okay, hetero different. Okay, so for example, we have NH4Cl, which is in solid phase, react to form NH2 gas and HCl gas. So here the reactant is in solid phase, and but however the product are in gaseous phase. Okay, look at this one. The water is in liquid phase. However, after the reaction, the water is in the gas phase. So this reaction we call is heterogeneous equilibria. They are in the heterogeneous system where the reactant and the products are in different phase. So that is the types of equilibrium reaction, homogeneous and heterogeneous. So remember, homogeneous is the reaction where all reactant and product are in the same phase. However, heterogeneous equilibria is the reaction in which the reactant and products are in different phase, which means that they can exist in more than one phase. Okay. So now we are going to look at the expression for equilibrium constant. So last time we have looked at the general equilibrium constant, which is K equals to the concentration of product over concentration of reactant, blah blah blah, right? So today we are going to look at the types of equilibrium constant. So basically, the expression for equilibrium constants can be divided into two. The first one is in terms of concentration, and the second one is in terms of partial pressure Kp. So in terms of concentration Kc can involve for the gases, aqueous state, semua state lah boleh. Okay, but in terms of partial pressure Kp, it is only applicable for the gases state only. Okay, so now So now the expression for equilibrium constant can have for homogeneous equilibria and heterogeneous equilibria. And we are going to look at this part one by one. Okay, let's look at for homogeneous equilibria first. Okay, for homogeneous equilibria, we are going to look at the example for N2O4 gas decomposed into NO2 gas. Okay, so now both are in the gas phase, so that's why it is in homogeneous equilibria system. So now we are going to look at the expression for equilibrium constant in terms of concentration and in terms of partial pressure for this reaction of homogeneous equilibria. So let's look at the equilibrium constant in terms of concentration. So we know that the Kc, so this is for the equilibrium constant in terms of concentration. So we put the what we call this subscripts. Subscripts C dekat K, dekat the capital letter K to denote that this is the equilibrium constant K in terms of concentration. Okay, in terms of concentration. So Kc is equals to, so this is product, so this is the reactant. So product first, baru reactant. So the concentration of NO2, since dia ada dua dekat sini, so we put 2 here. Okay, so the concentration of NO2 to the power of 2 over the concentration of reactant N2O4, since dia tak ada coefficient depan dia, so tak ada apa-apa. So that's it for the Kc for this chemical equation. So Kc is equals to concentration of NO2 to the power of 2 over concentration of N2O4. So this is for the expression for equilibrium constant in terms of concentration for this reaction. So let's look at the expression for equilibrium constant in terms of partial pressure. So, in terms of partial pressure, so we will gantikan in terms of concentration jadi partial pressure, so dia akan jadi like this. So, the concentration, so the equilibrium constant K in terms of partial pressure P here is equals to bracket, round bracket, tadi dia square bracket, right? So, now dia round bracket, partial pressure P in partial pressure of NO2 to the power of 2 because dia ada coefficient 2 dekat sini over partial pressure of N2O4, tak ada to the power lah sebab dia tak ada coefficient, there is no coefficient in front of N2O4, right? So this is how you write the expression for equilibrium constant in terms of partial pressure for this homogeneous equilibrium, which is Kp is equal to PNO2 to the power of 2 divided by partial pressure N2O4. Okay. So now we are going to look at the heterogeneous equilibria. Okay. So for the heterogeneous equilibria, so we are going to look at this example. NH4Cl solid will react to form NH3 gas plus HCl gas. So, in terms of concentration, we are going to include the product over gas, concentration of product over gas. However, since the reactant is in solid state, so we do not include it in the equilibrium constant expression. Okay, we will see why it is not included after this, okay? So, since the concentration of pure solid and liquid are excluded in this equilibrium constant expression, so we are going to only include the product punya concentration. So, for heterogeneous equilibria, in terms of concentration Kc, the expression for Kc is equals to concentration of NH3 times the concentration of HCl only. We are going to include the gas phase only. The solid is not included. Okay, and in terms of partial pressure, Kp is equals to partial pressure NH3 times the partial pressure of HCl. Same as well, we are not going to include the solid. Okay. So now, the reason why the concentration of pure solid and liquid are constant and excluded in the Kc or Kp is because the concentration of pure solid and liquid do not change significantly and remain constant at constant temperature. So means that regardless of the amount of the the solid, the concentration remain the same. So it means that the amount per unit volume is the same. So the density of the solid will remain the same at the temperature. So which means that the concentration will not change as well. So that is why we will exclude the concentration of pure solid and liquid since it did not give any significant change in terms of concentration. Okay, so kita ignore je the pure solid and liquid punya concentration. So we just include the gases and aqueous punya phase sahaja. Okay, for Kc and Kp. Okay. And in terms of partial pressure, we does not include also because partial pressure is for gases or is applicable for gases state only, kan? Dekat atas ni applicable for gases only. So since this is solid, so we cannot include it. Okay. Alright, so I hope that you understand how to write the expression for equilibrium constant in terms of concentration and in terms of partial pressure for both homogeneous system and heterogeneous system. Okay. Okay, remember, okay? Alright, so now we are going to look at the notes here. Okay, so remember that the equilibrium constant expression Kc and Kp are also called equilibrium law expression. Okay, and the P here yang dekat Kp punya equilibrium constant is equals to the equilibrium partial pressure of the gas. And usually we will use the unit of the pressure in terms of ATM usually. Okay, and remember that the Kc, the equilibrium constant in terms of concentration and partial pressure, Kc and Kp are dimensionless, which means it has no unit. Okay, Kc and Kp has no unit. And this is the rules that you must obey for Kc and Kp. First, you need to specify balanced chemical equation. So, mesti balance the chemical equation first. And then you have to include the phase of each reactant and product. So, in the balanced chemical equation, you have to include the phase of each reactant and product. And after you calculate the value of Kc and Kp, make sure you include the temperature. Okay. So, next, to find the value of partial pressure, equilibrium partial pressure, we need to assume the gases behave as ideal gas. So, we're going to use the equation PV equals to nRT, where the partial pressure P is equals to N over V times RT. Okay, so these are the notes that we are going to take note when we are doing this equilibrium constant expression. Okay. So now, let's look at the relationship between the Kc and Kp. So first, we are going to consider a general expression AA plus AA in gas phase plus BB in gas phase react to form CC in gas phase plus DD in gas phase. So remember, so the syarat for Kc and Kp, we must have a balanced chemical equation, include the phase of the every product and reactant. So we know that the relationship between Kc and Kp is equals to Kc times RT to the power of delta N, where delta N is the number of moles of gaseous product, is minus with number of moles of gaseous reactant. So maksudnya is equals to small letter C plus small letter D minus small letter A plus small letter B, because the small letter is they represent the coefficient stoichiometry as well as the moles of the product and the reactant. So that is why delta N is equal to C plus D minus A plus B. Okay, and R here we usually use the universal gas constant of 0.08206 liter ATM per mole per Kelvin. Hence why we always use the unit partial pressure of ATM. Okay, and T here is the absolute temperature Kelvin, and we use the temperature in unit Kelvin. And in most cases, the Kp is not equal to Kc. Okay, in most cases. Alright. So now, let's look the steps on how you want to derive the equation to get Kp equals to Kc RT to the power of delta N. Okay, first step, we are going to write the expression of Kc and Kp. So note that we are going to consider this general chemical equation. Okay, so AA plus BB plus C, form CC plus DD. Okay, so we write the expression for Kc and Kp. So for Kc, it is equal to the concentration of C to the power of C times concentration of D to the power of small letter d over, so this is product kan, so over the reactant, concentration of A to the power of small letter a times the concentration of B to the power of small letter b. So this is how you write the expression of equilibrium constant in terms of concentration. Next, for Kp, Kp is equals to partial pressure C to the power of small letter c times partial pressure D to the power of small letter d over partial pressure of A to the power of small letter a times partial pressure B to the power of small letter b. So this is how you express the concentration of partial pressure, the equilibrium constant in terms of partial pressure. Okay, I'm sorry. Okay. So after you write the expression of equilibrium constant in terms of concentration and partial pressure, now we are going to write the expression for each partial pressure. Okay, so we know that we need to assume the gases all behave as ideal gas to use this PV equals to nRT equation. So now we can have the formula for partial pressure is equals to N over V times RT. So we are going to substitute inside each of the component for A. So for partial pressure A here, partial pressure A is equals to number of mole A over V times RT. So we know that the concentration, concentration is equals to number of mole over volume, right? So we know that N A over V is equal to concentration A. So N A over V is A, concentration of A times RT. Same goes to PB, PC, and PD. For partial pressure B, partial pressure C, and partial pressure D. So we will convert the number of mole B over volume into concentration B. Okay, nampak kat sini kan? Okay, so now after we write the expression for each partial pressure, the next step is we are going to substitute the partial pressure expressions in the Kp expression. So we know that Kp is equals to Kc times RT to the power of delta N. So we put here, So we know that Kp is equals to partial pressure C times partial pressure D over partial pressure A times partial pressure B. Okay. So we masukkan all the expression in dalam tu. So now PC we know that the partial pressure C is equals to concentration of C RT to the power of small letter c times concentration of D times RT to the power of small letter D over concentration of A times RT to the power of small letter A times concentration of B times RT to the power of small letter B. So now kita akan keluarkan RT ni. We take out the RT and satukan dia. So dekat sini kita akan dapat macam ni. Kp is equals to concentration of C times concentration of D over concentration of A times concentration of B times RT to the power of, nampak tak the coefficient kat sini? The superscript dekat atas ni. So dekat sini kita akan cakap C tak plus D minus A plus B. This is mathematics, right? So times RT C plus D minus A plus B. So dekat sini, this one is actually delta N. So this is actually the number of mole of gases product minus the number of mole of gases reactant. So that is why we get the relationship for Kp and Kc, because this is actually this one so this is actually Kc. Betul tak? So this is actually Kc. So now we know that Kp is equals to Kc RT delta. And so begitulah kisahnya on how we are going to derive the Kc and Kp to form this equation. Okay, so it's very simple. Okay, so remember that delta N is equal to moles of gases product minus moles of gases reactant. So remember that, okay? So now, okay, this one it said that dia nak tunjukkan yang Kp pun boleh ada equals to Kc. So when the delta N is equals to 0, so we can say that Kp is equals to Kc 0.08206 T to the power of 0. Bila delta N equals 0, so include kalau kita ikut matematik punya rules, dia akan jadi 1 kat sini kan. So Kc times 1 equals to Kc. So that is why Kp is equals to Kc. Okay. So now we're going to answer the few of the tutorial question. Okay. So let's look at question 3. So question 3, it says that at equilibrium, there are 2.5 moles of sulfur dioxide, 1.35 times 10 to the power of negative 5 moles of oxygen, and 8.7 moles of sulfur tridioxide present in a 12-liter flask. Okay, so this is the volume. So this is the number of mole, number of mole, number of mole. So calculate the equilibrium constant in terms of concentration Kc for the reaction at 700 degrees Celsius. So what is the first step that we are going to do is we are going to find the concentration for each of the component, because we need to find the equilibrium constant in terms of concentration. So we need the concentration. So to find the concentration, we know that concentration is equals to number of mole divided by volume. So what we need to do is to find the concentration of sulfur dioxide is 2.50 moles divide by volume dia liter kan, 12 liter. So we are going to get the concentration is equals to 0.2083 molar. Okay, and besar. For oxygen, same as well, 1.35 times 10 to the power of negative 5 mole divided by 12.0 liter. So it is equals to 1.125 times 10 to the power of negative 6 molar. And lastly, for SO3, 8.7 0.70 moles divided by 12.0 liters, so it will be equal to 0.725 molar. So now we have the concentration for all the components. So now we can we can find the Kc. So we know that Kc is equals to, equilibrium constant is equals to the product of concentration of product be divided by the concentration of reactant. So product here, so we know that concentration of SO3 to the power of 2 divided by concentration of SO2 to the power of 2 times concentration of oxygen. Okay? Alright, so now kita akan substitute the values that we have find earlier, masukkan dalam this. So dia akan jadi 0.725 to the power of 2 divided by 0.2083 squared times 1.125 times 10 to the power of negative 6. Okay. So, Kc dia adalah, kira lah ni. Berapa? So, we will get the answer for Kc is 1.076 times 10 to the power of 7. And since Kc and Kp has no unit, so no need to put unit. Okay, so 1.06 times 10 to the power of 7. So this is how you find the Kc for this question. Okay, so now let's look at question number 4. So for question number 4, dia suruh cari equilibrium constant in terms of partial pressure pula. So dia bagi dah. Dia bagi direct sangat soalan ni. So dia bagi partial pressure for PCl3, oxygen and POCl3 at equilibrium of 5.05, 2.5 and 101 kPa respectively. Calculate the equilibrium constant Kp for the reaction. So dekat sini kita akan terus je guna this unit because semua sama kan unit kan. Kalau unit lain-lain, so we will prefer ATM, but since semua kPa, so we just use that. So we know that the expression for equilibrium constant in terms of partial pressure is equals to product over reactant. So partial pressure of POCl3 to the power of 2 divide partial pressure of PCl3 to the power of 2 times partial pressure of oxygen. Okay, so now we have the value for each that. So POCl3 101, so 101 squared over 5.05 squared times 2.50. So we will get the answer is 160. Okay. Alright. Alright. Now, let's look at question number 5. It's very simple. Question 3 and 4 sangat simple, okay? So, should be no problem. So, question number 5 said that, Allah, berbondo. Okay. Question number 5 said, at 25 degrees Celsius, H2O liquid reach equilibrium according to the equation H2O liquid equilibrium with H2O gas. So calculate the Kp and Kc for the reaction. the vapor pressure of water at 25 degrees Celsius is 23.8 torr. So we need to convert the vapor pressure in terms of ATM since we are going to use this equation R here, right? So we tukar ATM. So we know that PH2O is equals to 23.8 torr times, you know that 1 ATM is equal to 760 torr. So we call partial pressure of water here is equals to 0.0313 ATM. So now we can find Kp. So Kp is this one only again because partial pressure, the equilibrium constant in terms of partial pressure should applicable for gases phase only. So Kp here is equals to partial pressure of H2O. So we know that partial pressure of H2O is 0.0313. Okay, so now we can find the Kc because we know that Kp is equals to Kc times RT to the power of delta N. And now we can what we call it, kita akan terbalikkan lah sebab dapatkan Kc kan. So sekarang ni kita akan dapat Kc is equals to Kp divide by RT to the power of delta N. So that's why kita dapat negative sign here. Okay. So that is why we got the negative sign there. So now kita dapat Kp is equals to 0.0313 times R, we use 0.08206 liter ATM per mole per Kelvin times dengan the 25 degree Celsius. So Kelvin 298 Kelvin. So we will get Kc is equals to 1.28 times 10 to the power of negative 3. Okay. So that is how you get Kc. Okay, we find the Kp first, then we find Kc. Okay. Alright. So this is how you answer question number 5. It's very simple. So now we are going to look at question number 6. Okay, I hope you understand. Okay, kalau tak faham, kita boleh you boleh replay balik video ni. Okay. So now for number 6, it says that the nitrogen dioxide dimerized according to the equation. So 2 nitrogen dioxide gas dimerized into N2O4 gas. So dia bagi Kp is equals to 7.13 per ATM. Supposedly Kp the dimensionless, they no unit. I don't know why this question have unit. Okay, so at equilibrium, the partial pressure of nitrogen dioxide in a container is 0.15 ATM. So this is the partial pressure of nitrogen dioxide, 0.15 ATM. Calculate the partial pressure of N2O4 in the mixture. So sekarang kita dah tahu Kp, kita dah tahu partial pressure of NO2. So we know that Kp, dia punya expression there is equals to product over reactant. So partial pressure of N2O4 over partial pressure of NO2 squared. We know this. Okay. Is equal to 7.13. Okay. So Kita dah tahu ni, kita boleh buat macam ni. Okay. So, 7.13 is equals to Pn2O4 over 0.15 squared. So, we will get partial pressure of N2O4 is equals to this times this, right? So, 7.13 times 0.15 squared, we will get 0.16 atm. So this is the partial pressure. Because here we will say that the partial pressure of N2O4 at equilibrium is 0.16 atm. Okay. Alright. So this one is also very simple. Question tutorial sangat-sangat simple. Okay, nanti dekat dalam past year soalan dia lagi mencabar. Okay, more challenging questions in the past years. So this is just the introduction. Okay, nice. We look at question number 7. Okay, question number 7 says that at equilibrium in the following reaction at 60 degrees Celsius, the partial pressure of bromine gas is 0.6 atm. Derive Kp equals to KCRT to the power of 1 over 2. And what is the value of Kp for the reaction of ferrum FeBr3 from FeBr2 plus 1 over 2 bromine gas? Okay, first we want to write the expression for Kp and Kc. So remember that for the equilibrium constant Kp and Kc, we do not include the solid part. We just include the gas part, right? So what we can do is, we can say that for Kc is equals to the concentration of Br2 to the power of 1 over 2. Okay? Allah, why is this happening? Okay. Concentration of Br2 to the power of 1 over 2. And for Kp is equals to partial pressure of Br2 to the power of 1 over 2. So we have Kc and Kp now. So now, second step is we want to write the expression for the partial pressure. So partial pressure here. So we know that. So we will assume bromine gas behave ideally. So Br2 VBr2 is equals to NBr2 RT. Okay, so we can say that PBr2 is equals to NBr2 RT over V bawah-bawah kan? So over VBr2. Okay, so we know that NBr2 over VBr2 is equals to concentration of Br2. So you can say that now PBr2 is actually equals to the concentration of Br2 to the power times RT. So this is the expression for partial pressure Br2. Okay, now we have the partial pressure Br2 in terms of concentration. So we need to substitute the expression of partial pressure into the expression of Kp. So we know that Kp is equals to partial pressure of Br2. So kita masukkan ni. So partial pressure of Br2 is here. So Kp is equals to Br2 to the power of 1/2 times RT to the power of 1/2. Sebab kalau kita masukkan dia, kita akan expandkan dia. So, each of this akan dapat 1/2 to the power of 1/2. Mathematics, okay, mathematics. So, dia akan dapat Kp now. So, we know that Kc is equal to concentration of Br2 to the power of half. So, sama tak? So, kita akan substitutekan dia jadi macam ni. So, Kp now is equals to Kc RT 1/2. So, this is how you write. So, this is how you derive the equation to find Kp equals to Kc RT to the power of 1/2. Okay. So, now, last soalan dia kata, what is the value of Kp? So, kita nak cari Kp pula. So, we know that dia bagi kita the partial pressure of bromine gas is 0.6 kan. So, kita boleh pakai this equation. Okay, so Kp is equals to partial pressure bromine to the power of 1/2. So, partial pressure of bromine is 0.6. 1/2. So, we will get 0.775. So, Kp is 0.775. Okay. So, it's very simple. Kalau, if we have the value of Kc, we can use this equation formula. But since we don't have the formula, the value of Kc, so we can use this expression lah. So, Kp equals to partial pressure Br2 times 1/2 to the power of 1/2. Sebab apa? Dia bagi kita partial pressure of bromine gas. Okay, so we can use this to find Kp as well. Okay. So, last question before we end this class. So, it says that consider the following equilibrium at 25 degrees Celsius. We have 2 mole of sulfur dioxide gas react with 1 mole of oxygen gas to form 2 mole of sulfur dioxide gas. And dia bagi kita Kp is equals to 3 times 10 to the power of 5. So, calculate the Kc for the reaction. So, we know that Kp is equals to Kc times RT to the power of delta N. So, bila kita pindahkan jadi Kc divide by Kc is equals to Kp over RT to the power of N. Kita akan dapat macam ni. Kc equals to Kp RT negatif delta N. Kan? Sebab dia dah bawa ke bawah, so dia kena negatif lah. Betul? So, kita akan tahu delta N is equals to moles of gases product minus moles of gases reactant. So, it is equals to moles of gases product 2 kat sini, right? 2 minus gases reactant 2 plus 1. So, it's equals to 2 minus 3. So, equals to negative 1. So, Kc is equals to Kp kita tadi. 3 times 10 to the power of 5 R 0.08206 T 298 okay, this one to the power of negative 1, so dia positive 1 lah, betul? So dia akan dapat equals to, you after you substitute everything, kan, you will get KC is equal to 7.336 times 10 to the power of 6. So this is what you get for KC. Okay. Alright. That's it. Okay. So this part 1 of chapter 6.2 is quite simple. As long as you know the types of equilibrium, there are homogeneous and heterogeneous, and how there are two ways to express the equilibrium constant. First one in terms of concentration, second one is in partial pressure. And take note that we does not include the pure solid and liquid phase in the equilibrium expression Kc and Kp. So we just include gases and aqueous state. But for partial pressure, we just include gases state only. Okay, and yeah. And you have to know how to derive the equation Kp equals to Kc times RT to the power of delta N. Okay, so that's it. So that's it for chapter 6.2 part 1. Okay, so we are going to learn the next chapter 6.2 part 2 in the next video. So I hope that you guys are able to understand this part easily, because this is, I think, quite an easy part lah. Okay, so if you don't understand anything, please message me in Telegram, okay, and ask me so that I know that, oh, you guys dah faham. Okay, so yeah, that's all for today. Thank you for watching this video, and I hope that you have a very nice day ahead. Alright, thank you, and Assalamualaikum. Bye-bye.